This is example number 3 from lesson 6.4 using the quadratic formula. Between example 1 and 2 we were able to see parabolas that had 2 roots or 1 root. In this case we are going to connect a parabola that has no real roots. So we're given the parabola has an equation y equals x minus 2 squared plus 3. And we are going to state the coordinates of the vertex, which we can get easily because it's already in vertex form, the equation of the axis of symmetry, and the direction of opening. And all of these things we can get without doing any calculations. After that we'll look at B. We're going to determine the x-intercepts, and we're going to verify using the quadratic formula, and then we will sketch the parabola. So the parabola that we are given is already, the equation is already in vertex form. So our vertex we can right away just say is h and k. So our vertex, the x-coordinate is 2, the y-coordinate is 3. For the axis of symmetry, well, the axis of symmetry is the line x equals, and it goes through the vertex. So the vertex is at x equals 2, so the line of symmetry must be x equals 2. Again, that's the line that goes right down the middle, crosses through the vertex, and since our vertex is at 2, 3, our axis of symmetry must be x equals 2. Direction of opening, I look in front of my brackets here, my squared binomial. Coefficient a is positive, it's positive 1, so this opens up. B of example 3 asks us to determine the x-intercepts. Well, just a quick look at the sketch over here. This is the sketch of our parabola. If the vertex is at the point 2, 3, and the parabola opens up, does it ever cross the x-intercept? The answer to that, of course, is no. There are no x-intercepts in this case. There are no x-intercepts. Now that's not quite sufficient, doing it by the graph and just judging it by the equation that we're given. So we're going to verify that using the quadratic equation, the quadratic formula, and we're going to find out what happens. So in order to use the quadratic formula, first of all, this needs to be rewritten in standard form. So let's do a little bit of math on this. This is a binomial squared, and I know that that expands to be a squared, and over here we're going to have b squared, and in the middle we're going to have 2ab. So we're going to have minus 4x, and on the outside we still have plus 3. I can combine like terms, leaving us with the parabola in standard form, x squared minus 4x plus 7. Well, now that I have this, I know my parameters. My coefficients, a is 1, b is negative 4, c is 7, and now I can go ahead and plug them into the quadratic formula. Negative b, plus or minus, square root of b squared minus 4ac over 2a over 2a. It's a tough decision when a teacher has to sing on video something that won't be destroyed. Okay, the beauty of the quadratic formula is that I just need to take my parameters a, b, c and plug them in, and I will get the solutions for this equation. So negative b, well, b is negative 4, so I have negative 4, that's positive 4, plus or minus the square root of b squared. I want to make sure I keep this negative 4 in brackets. The negative belongs to the 4, so there negative 4 is going to get squared, minus 4ac. And that's all getting multiplied together over 2 times 1. Let's quickly simplify the easy stuff here in this bracket. We've got negative 4 times negative 4, which is positive 16. And we're going to have minus 4 times 1 is 4. 4 times 7 is 28. and this is over 2. Let's reduce what's under the square root symbol here. 16 take away 28 is negative 12 over 2. Now, I've run into a problem. You can see under the square root is a negative number. There is no such thing as the square root of a negative number. There is no number whatsoever that can be multiplied by itself to equal negative 12. Can't happen. So this is undefined, and there are no real roots. If there are no real roots, there are no real roots, period. Therefore, there are no x-intercepts. Now, we already knew that, but it was good to verify using the quadratic formula, and now we know what to identify. If we're using our quadratic formula and we ever end up under the square root with a negative value, we can be certain that this parabola will not cross the x-axis. The last part of the example here is to draw a sketch of our parabola. We've noted a couple things already, that the vertex is at 2, 3. So go ahead and put that on my graph. I know it opens up, so I will label it down below. It does open up, but we haven't talked about where it crosses the y-axis. It does have a y-intercept, and it's pretty easy to find out where that is. The y-intercept happens wherever x equals 0, right? So if we're looking across our x-axis, wherever x equals 0, well, that's where the parabola is going to cross the y-axis. So let's find out what happens here. What value of y will we be at when x equals 0? So I can just sub in 0 for x. Inside the bracket, I now have negative 2 squared plus 3. Negative 2 squared is negative 2 times negative 2. That's 4 plus 3, 7. So therefore, the y-intercept is 7. And I can go ahead and plunk that on my graph. That's also very helpful because I know that parabolas are symmetrical on both sides, and I know they're symmetrical over the axis of symmetry, which occurs at the vertex. So I know that if I go 2 units to the left of the vertex and I'm at 7, then the value of the parabola will also be 7 2 units to the right of the vertex. So if the point 0, 7 is on the parabola and my vertex has an x value of 2, then the point 4, 7 must also be on the parabola due to the symmetrical characteristics of a parabola. Now I can go ahead and sketch it, making sure I have a rounded bottom. Of course, my sketch isn't perfect, but it's not bad. And there you have it, with our vertex labeled, our 2 other points that helped us draw the curve, and again, no x-intercepts in this example. Throughout this unit, we've talked about applications of quadratics and quadratic equations. One of them is to model the path of a projectile. So in example 4, we're looking at the path of a basketball. After it is thrown from a height of 1.5 meters, so someone has tossed it from a height of 1.5 meters above the ground, it follows the path given by the equation h equals negative 0.25 d squared plus d 2d plus 1.5, where h is the height in meters and d is the horizontal distance in meters. We have 2 tasks. We need to figure out how far the ball has traveled horizontally to the nearest tenth of a meter when it lands on the ground, and we need to find the horizontal distance when the basketball is at a height of 4.5 meters above the ground. So first A. Okay, let's think about the parabola that will be made by the path of this basketball. We know that there is going to be ground level. Somewhere there's going to be ground level. And so when the parabola gets to here, well, right there it's hitting the ground, which tells us that it's going to hit the ground at an x-intercept. We don't know where it starts. I'm going to guess he tosses it up a little bit, and this is going to be our height of 1.5 meters where it all starts from. So our goal is to find our two x-intercepts. There's always going to be, well, there's not always going to be two, but in this case there is going to be two, but one of them is going to be irrelevant. Of course, the one behind the person who throws it. This one doesn't actually exist in this real life situation because our friend is throwing the ball from right here. Well, if the ball is going to hit the ground at our x-intercept, that's when the height is 0. So all I need to do is set h equal to 0, rewrite the right side of the equation without changing anything, and then solve. I notice right away that I have a negative decimal out in the front here, and I have a decimal in the back. These things aren't going to factor out all that nicely. So I'm going to just go ahead and use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. I know my parameters. A is negative 0.25, b is 2, and c is 1.5. So now all I need to do is plug those numbers into the quadratic formula, and I will get my two x-intercepts, one of which will be a real answer, one of which will not be, but we'll talk about that when we get there. So x equals negative b, that's negative 2, plus or minus the square root of 2 squared minus 4 times, and I know this is 1/4, and I'd rather work with fractions, so I'm just going to go ahead and rewrite that as negative 1/4 times, and this is 1.5, which is the same as 3 over 2, all over 2a. So 2 times negative 1 over 4. We can reduce this by multiplying some things together here. We've got negative 2 plus or minus the square root of 2 squared, which is 4, minus 4ac. So we have 4 times 1/4. Well, that ends up being 4 over 4, which is 1. And we have minus a negative number times a negative number, which is a positive number. So I have positive 1 times 3 over 2. Well, let's go back to doing a decimal here because it came out pretty nicely as 1.5, 3 over 2. And here we are left with 2 times negative 1/4. So that's negative 2/4, which is negative 1/2. And we can reduce this further. So we have negative 2 plus or minus the square root of 5.5 over negative 0.5. So this tells me that d, if I plug this into my calculator, d equals negative 2 plus the square root of 5.5 over negative 0.5, or d equals negative 2 minus the square root of 5.5 over negative 0.5. Now I can't eliminate one of my answers yet. I really should just plug them both into my calculator and then figure out which value of d makes more sense. So this first one, if I plug it into my calculator, reduces to approximately negative 0.7, and this one over here reduces to approximately 8.7. Now remember, our question was how far has the ball traveled horizontally when it lands on the ground? Well, it wouldn't make much sense if we had a negative value for the horizontal distance traveled before it lands on the ground. We're clearly progressing here in a positive fashion. So the final answer is the basketball has traveled a horizontal distance of about 8.7 meters when it lands on the ground. In the first part of this example, we had to find the value of d when h was 0, when the height of the ball was 0, when it had reached the ground again. But in the next question, we need to find the horizontal distance, so we're still finding the value of d, not x, finding the value of d, but this time when the basketball is at a height of 4.5 meters above the ground. So this time when I sub in, I'm not going to sub 0 for h, I'm going to sub 4.5 in for h, because I want to find out what d is. I want to find out what d is when h is 4.5. So the right side of my equation doesn't change just yet, 1.5. But this isn't in the form that we're used to putting in the quadratic equation, the quadratic formula. In fact, this won't work. If I plug in the same numbers as before, I'm going to get the same answer as before. We need to have this set equal to 0. In order to do that, we need to subtract 4.5 from both sides of the equation. I'm a little bit tight on space, so I'm just going to erase this. 4.5 minus 4.5 is 0, and 1.5 minus 4.5 is negative 3. So now I have a new equation that I can plug into our quadratic formula, and when I use this one, I will get the values of d where the height is 4.5 meters. Now because a parabola is symmetrical, it's likely that this is going to happen at two separate points. But we'll see what happens as we carry on. Alright, A is negative 0.25, B is 2, C is negative 3. And I can go ahead and sub those into my quadratic formula. So we have negative b, which is negative 2, plus or minus the square root of b squared, which is 2 squared, minus 4ac, all over 2a. Let's reduce what we can. Inside the square root, we have 2 squared, which is 4. And then we have 4 times a quarter, and they're both negative, so that's going to be positive 1. Positive 1 times negative 3 is minus 3, all over 2a. 2 times negative 0.25 is negative 0.5. And I'm still using x. We know that in this case x is being replaced by d, so d equals these things, d equals these things. So when we're finding x here, for this application, it's actually the horizontal distance, which is represented by d in this problem. So here we have our two answers. I can reduce this under the square root. 4 minus 3 is 1. The square root of 1 is 1, because 1 times 1 is 1. So we have two options here for d. Either d equals negative 2 plus 1 over negative 0.5, or d equals negative 2 minus 1 over negative 0.5. Over here, we get negative 2 plus 1, that's negative 1, over negative a half, well, that's positive 2. And over here, we get negative 2 minus 1, which is negative 3, over negative a half, which is positive 6. So the horizontal distances when the ball is at 4.5 meters in height is 2 meters and 6 meters. So our sketch is not to scale here. 1.5 is here and 4.5 is here. So that's not quite right, but it does show us where these things happen. This happens at 2, and this happens at d equals 6. I hope that this helps in doing your homework this evening. And please come to class with questions, and also be prepared for your quiz.